Hi everyone. So today we're going to continue on 11.5 Laplace Transform. And the problem here is that what we're going to do next is the following. So we have done quite a few different examples on the first order differential equation. But we do want to be able to do at least second order differential equation or even higher order differential equation. And you find that the process is actually quite straightforward when you apply Laplace transform, because you always basically going to go through the same exact process. You apply Laplace transform to both the left side and the right side. You rewrite all the Laplace transform of all the derivative into the Laplace transform of just the function y. And then you isolate the Laplace transform y, and then you have a fraction to the side. Then we'll do partial fraction decomposition to break it down, and then try to figure out from all those partial fractions what should the function y be. And it's actually very basic routine. And yes, some of the algebra involved can be a little harder to do, but the key is that you really don't do any derivative or integral in solving this equation. Okay, remember that's the key. And it is very surprising that you would think that solving a differential equation would require integration. But we actually try to avoid doing that. So today what we're going to start with is the following. In order to do a higher order differential equation, I need to know how to deal with the Laplace transform for those higher derivatives. So let's try to figure it out. So recall, when you do a Laplace transform of the derivative of a function y, that is equal to negative y of 0 plus s Laplace transform of y. Okay, so that's what we know. So that's the formula that we should know. And also I'm going to caution you that this formula is actually not on the formula sheet. That means it's something that you have to memorize. So now comes the question, what happens if I want to do y double prime? Well, let's start with the following. Suppose I just take this formula right here. What do I want to apply to y double prime? Well, then pretty simple. This is what you do. You just add a prime right there. And so therefore, consequently, you have to add a prime to both of these to kind of make it consistent. So therefore now we actually have a formula that allows us to deal with y double prime. That's easy, right? Well, not quite. Remember, the idea of using Laplace transform to solve a differential equation is to eventually get down to a point where you can identify the Laplace transform of y by itself, so that we can then use whatever on the other side to figure out what the function y should be. So therefore, the essence to this method is to be able to transform everything, all the derivative of y, into just the Laplace transform y, L of y. So this doesn't work here because I have a Laplace transform of y prime. Lucky for us, we know what the Laplace transform of y prime is. It's right there on top with the red box. So I'm going to go ahead and use that to help me figure it out. So that means this is equal to negative y prime at 0 plus s times Laplace transform of y, which is basically Laplace transform of, which is basically what I'm going to use a formula on top for, which is negative y of 0 plus s L of y. So if I distribute, I now have this formula. Actually, it's minus. And that is a formula that allows you to deal with Laplace transform of y double prime. And notice that it results in Laplace transform of y at the end, but it does require you to know two things, y of 0 and y prime of 0. Those are the initial condition. Now comes the next question. What if we now want to do y triple prime? What happened to y triple prime? Well, then pretty easy. That would just be basically be using y double prime formula Okay, but add a prime to everything. So therefore, maybe I'll start from this to kind of show you what to do. So here's my y double prime formula. And to find y triple prime, I'm going to do this. And once again, that would mean I have to do L of y prime again. So I'm going to do that. And that will give us this formula. Oh, is minus. And that becomes the formula for Laplace transform of y triple prime. Now, here comes the big question. Look at these three formulas. Can you see a pattern that will allow you to write out the formula for y quadruple prime? Okay, so let's see if we can see a pattern here. So this is what we know. We start with our Laplace transform. So maybe I'll title this Laplace transform of higher order derivative of y. So we start with the first one, which is Laplace transform of y prime. And we know that's equal to negative y of 0 plus s Laplace transform of y. So that will be this formula that we box in right there. And then we know our second derivative, y double prime, when I do a Laplace transform of that becomes negative y prime is 0 minus sy of 0 plus s squared Laplace transform of y. And we also did L of y triple prime, so I'm going to write that directly underneath. So that's equal to negative y double prime is 0 minus sy prime is 0 minus s squared y of 0 plus s triple L s cube L of y. So now comes the big question. Based on the pattern that's established here, can you now write out what is the Laplace transform of the fourth derivative of y? So what I would suggest you to do is pause the video and see if you can write that out. And then once you finish, you can then continue the video and see if you got it right. Okay? Alright, hopefully you have a chance to think about it. So let's see if we can write this out without actually go through the process. Okay, so that would be Laplace transform of the fourth derivative of y. So what would that be? So that would actually equal to this. So hopefully you got that right. And we can write out the fifth, the sixth, and so on and so forth. By repeating this process, we have the following formulas that will allow us to deal with Laplace transform of y to any derivative. Laplace transform of y to the nth derivative. That would equal to negative y to n minus 1 derivative as 0 minus s times y to n minus 2 derivative as 0 minus s squared y to the n minus 3 derivative as 0 minus that pattern continue until we get to s to the n minus 1 derivative. Oh, actually, I'm sorry. S to the n minus 1 power times y to the 0 plus s to the nth power Laplace transform of y. So this is the formula that you kind of need to know. Even though this formula is written for y, Laplace transform y to the nth derivative, but we highly unlikely use it past third derivative. We are not going to do like really high order differential equation, so therefore it won't be that high. You should definitely memorize y prime, y double prime, and maybe y triple prime, and that's usually good enough. But you know, definitely also know this formula just in case you do need to use it. So now what I want to do is to maybe show you how to do a problem, a second order differential equation instead of a first order, and show you what happened to this one then. All right, so let's give it a try. So here's the problem, solve by Laplace transform. Oops, forgot Laplace. And here's the equation, y double prime minus y prime minus 2y equal to 3e to the t. And then we have our initial condition, y of 0 equal to 1, and y prime of 0 equal to 0. So hopefully the y prime of 0 equal to 0 would help us simplify the problem a little bit better, but we'll see. All right, so let's go for it. So y double prime minus y prime minus 2y equal to 3e to t. Remember, the process of solving this equation using Laplace transform is pretty much exactly the same as all the other one. You go through the same exact step, just the step might be more difficult, but it's the same exact step. And you don't really have to think about what you need to do. You just go through the same exact thing. So that means I'm going to do Laplace transform of y double prime minus y prime minus 2y. And that's equal to Laplace transform of 3e to the t. So remember, the 3 is a constant, so you can pull that out. And so it's basically doing Laplace transform of e to the t. So what happened to this thing? Well, let's see. So Laplace transform is linear, so therefore this means on the right side, well, actually left side, is Laplace transform of y double prime minus Laplace transform of y prime minus 2 Laplace transform of y, and that's equal to 3 over s minus 1. Because that's just equal to 3 times 1 over s minus 1. So now a matter of just clean up the Laplace transform here. So let's start with the y double prime. The Laplace transform of y double prime would equal to negative y prime of 0 minus sy of 0 plus s squared Laplace transform of y. Minus Laplace transform of y prime. So that would be equal to negative y of 0 plus s Laplace transform of y. And then minus 2 Laplace transform of y, and that's equal to 3 over s minus 1. So y prime of 0 is 0, so that goes 0, and y of 0 is 1, and so that also goes to 1. So if I'm looking at this correctly, that gives me negative s plus s squared Laplace transform of y. Minus negative 1 become plus 1, and minus s Laplace transform of y minus 2 Laplace transform of y equal to 3 over s minus 1. So now let's see what we need to do. So I'm going to go and collect all the Laplace transform of y together, and that gives me s squared minus s minus 2 Laplace transform of y equal 3 over s minus 1. I'm going to go and move the minus s and the plus 1 over. So that's what I got. And now what I need to do is combine the right hand side together. You do have to combine them all into a single fraction. Then you can properly separate them into partial fraction. So that is something that you have to do. So therefore, it's a lot of algebra that you have to get done. So this, I'm going to go and do this. I'm going to go and put this over 1 and multiply this by s minus 1 over s minus 1 so that I have a common denominator to combine them together. So if you do that correctly, you have s minus 1 on the bottom, and the top will be 3, and s minus 1 times s minus 1 is s squared minus 2s plus 1, so plus 3 will be plus 4, so s squared minus 2s plus 4. And now, our final step, our Laplace transform of y would equal to s squared minus 2s plus 4 over s minus 1 times s squared minus s minus 2. So now we finally get down to what the Laplace transform of y is, which equal to this fraction. But of course, obviously, the problem here is that we don't know what function of y would give me this fraction, because this fraction is basically multiple fractions combined together. That's the problem. So now what we're going to do is our partial fraction decomposition. So once again, this one is actually not too hard to do. So we're going to go and try to do this one and then finish up the problem. Okay. So we're going to look at this partial fraction right here. Oops. So notice s squared minus s minus 2 can be factored. That actually factor to s minus 2 and s plus 1. So therefore, meaning that this fraction actually will have 3 partial fractions. So I'm going to go and list them. You'll go and go do this. S minus 2 plus b over s minus 1 plus c over s plus 1. And if I combine these 3 fractions on the right-hand side together, I would have this. So when you combine all of them together, that's what you go get. And remember, once you have this step, because the denominator is the same, that implies the numerator are the same. So therefore, now I have this equation that we're going to try to use to figure out a, b, and c. And no, you should not multiply these parentheses out. So how do we go about solving this? Well, pretty simple. We're just going to go do the same exact thing like we did before. I'm going to first start by letting let s equal to 1. Then what I have will be 1 minus 2 plus 4. That would be 3. Notice that the a would go away because you have s minus 1 which go to 0. B would stay, but C would also go away. So therefore, it just becomes B multiplied by 1 minus 2, which is negative 1, and 1 plus 1 is 2. So therefore, tell me that B must equal to negative 3 over 2. Now we're going to go ahead and do a second number. Let's S equal to maybe 2. So if s equal to 2, then this would be 4 equal to, a would stay, it would become 1 times 3. And then b and c would both go away because the s minus 2 factor. So therefore, tell me that a must equal to 4 over 3. And finally, we're going to let s equal to -1. And if I do that, I would actually get 7, because 1 plus 2 plus 4. And that equal to A will be gone, B will be gone, but C will stay, so we'll put on C. And -1 minus 2 is -3, and -1 minus 1 is -2. So therefore it becomes 6, so C would equal to 7/6. And so what does that tell me? That tells me that our Laplace transform, L of y, which was equal to this massive fraction before, s squared minus 2s plus 4 over s minus 1, s minus 2, s plus 1, is actually equal to the following. Is equal to, let's see, a is 4/3, so 4/3 times 1 over s minus 2 plus, actually minus, because b is negative, minus 3/2 times 1 over s minus 1, and then plus 7/6 times 1 over s plus 1. So therefore imply that our function y should be made up of 3 different functions. Okay, which kind of makes sense. The reason why it makes sense because our differential equation is second order, so therefore indicate that the homogeneous solution should have 2 terms, and then we have one single function in the non-homogeneous function in the non-homogeneous equation f. So therefore imply that while particular solutions should have only 1 term, so therefore total up to 3 terms, which is exactly what we have right now. So what is the answer y then? Well, y would equal to 4/3. 1 over s minus 2 must come from e to the 2t. Minus 3/2. 1 over s minus 1 come from e to the t. Plus 7/6. And 1 over s plus 1 must come from e to the negative t. So that's my equation. All right. So now come another kind of same question. Our differential equation is y double prime minus y prime minus 2y equal to 3e to the t. So therefore I can say this is d squared minus d minus 2 of y equal to 3e to the t. So once again, same exact question I asked on the last problem. What if I take d squared minus d minus 2 and put in 4/3 e to the 2t? What should I get? And if I do d squared minus d minus 2 of -3/2e to the t, what should I get? If I say d squared minus d minus 2 of 7/6e to negative t, what should I get? Okay, so what I would like you to do, you definitely need to understand what they are, because you need to be able to identify the terms within your solution, where they come from, the homogeneous or the particular solution, so that you know how to answer this question. So I would strongly recommend that you pause the video, try to figure it out, and then maybe go ahead and do the linear operator on those 3 things and see for yourself if it match what you think they should be. Okay? And if not, then you have to rethink and try to understand what's going on. All right? So go ahead and take a minute to do that. So if I'm looking at this correctly, since our differential operator is d squared minus d minus 2, therefore imply that our characteristic equation is this. And that gives us 2 roots. Okay, which is 2 and -1. And so therefore identify the 2 homogeneous solution term must be e to 2t and e to negative t. Therefore tell me that these 2 things must come out to be 0. But they are the 2 homogeneous solutions. And therefore tell me that this one must come out to be what f is. There you go. Alright, unfortunately that's all the time I got for this video. We're going to continue some more on the next video, okay? I'll talk to you guys later. Bye-bye.